letter analysis, we need a transfer function that we deal with, that we use to, or a state space model. So when this started to take the attention of the community, it started very early right after this. They immediately realized that we need to approximate this thing by a finite dimensional approximation. And it continued until you will find papers in the 90s, so from the 30s to 90s, continuous work from the community for better approximations of simply Wagner function in the time domain and Tedorson function in the frequency domain. What's the best approximation? So one approximation that we mentioned last time was 5S. So unlike Tedorson, Wagner doesn't even have an analytical expression to begin with, right? So it really deserves to be approximated by something analytical. So this was one of the best approximations, at least because it's exponential. And we will see immediately why, if it's exponential, will be good. And that's the thing. I'll hopefully move fast. I need to finish this part. If you have this is the step response. The output due to a step input. Can you get the transfer function? I have the output and I know the input. It's unit step. Just divide them by, you get your transfer function, right? But we divide them in the Laplace domain. So let's get the Laplace of this guy. So the Laplace of this guy is what? So the transfer function, which we call d of p, will be the Laplace of this guy divided by 1 over s, or 1 over p, right? Please don't confuse the s here. Okay? Our Laplace is p. So our transfer function, simply, the Laplace of 1 is what? Laplace of 1 is what? Laplace of 1 is what? 1 over s. Yeah, so 1 over p, that's right. Minus Laplace of exponential is 1 over s, which is b, plus the exponent. The same here. Look at how easy it is. Divided by 1 over p, we got our transfer function. Okay? I'll just rearrange things. So you follow the steps, okay? Just try to multiply up and down. I'll not waste time here. So this is 1 minus a1 minus a2 p squared plus p. This is the coefficient of s squared in the denominator. And here is the coefficient of s. It's what? It's b1 plus b2, I guess. Plus a1 b1 plus a1 b2 plus a2 b1. Yes. And the free term is, let's see what's the free term. Anyway, downstairs, what do we have? We have p squared. We have b1 plus b2 p, and we have b1 b2. So this guy is b1 b2. Okay? So this is your transfer function. Just check it out. Do the math here. You will get it very easy. Just a minute. What's your DC gain? First of all, what's the value of the DC gain expected? What's the value of the DC gain expected?
1/2.
The DC gain is unity. Right? This is what we found here, right? The DC gain was unity, the high frequency gain is half, right? Okay, how do you get the DC gain from here? It's very easy. How do you get the DC gain? Equals 0. So it's 1, right? B1, B2, B1, B2. And what about the high frequency gain?
1 times a1.
Exactly, it's this guy. So this is why in every approximation like this, you will find these guys, the addition of these guys is half. So this is 0.165, 0.335. Okay? We have a transfer function. So you can do like this in MATLAB. You can do, here is my numerator, is the coefficients. 1 minus a1 minus a2, comma. This guy, b1 plus b2 plus a1 b2 plus a2 b1, comma, and the free term. So this is your numerator, and here is your denominator. Is the coefficients of the denominator. It's 1 and b1 plus b2 and B1 times B2, you have n, and then your transfer function, the arrow system or whatever, is TF. It's a transfer function of num and then. You can do whatever. You can do booty. You have a transfer function now. You can do booty, which is, if you do booty for this, you'll get what? You do booty for this, you'll get what?
C of k.
Exactly, it's the dorsal function, right? Frequency response. And you can do step response. You recover the Wagner. You can do impulse. And more generally, you can do LSM, linear simulation, of your arrow system. And any input you like as a function of time, over the time, and we have to have zero initial conditions. So this is the x naught, so it's zeros of 2 and 1. Okay? So you can now simulate it to any input. It's very convenient. And moreover, you can do transfer function to state space. Right? You can have a state space model. We will do the state space now together analytically because we will need it for flatter computation later. But you have a transfer function. Right? Now you have this guy is no longer 2 pi between alpha and left. Now you have a real dynamical system. It's a transfer function. Okay? Any question? So you got a transfer function for aerodynamics. This is a good thing. Any question? I'll do the state space model now. So given a transfer function, I'll do a state space model. We do it like this in dynamics and control. But we'll do it analytically. Actually, MATLAB can do it for you, like I said, but I'll do it analytically because we will need it later, and I will finish there. Any questions so far, please? Please, if you have a question. Any question? Okay, so let's do the transfer function. At the end of the day, my d of p was something like n2p squared, right? n1p, these are the coefficients, n2, n1, and the n naught, divided by this was p squared plus d1p plus d naught, right? Where these coefficients are defined obviously as above. Here is the value of A1 and A2, and last time I gave you also the values of B1 and B2. So if you have a transfer function like this, how to get a state space model, and this is a trick actually, so not every student of dynamics and control likes to do it, but because we don't immediately multiply both sides. This is, remember, this is output, which is left circulatory divided by input. We don't immediately multiply both sides. You cannot, it doesn't work like this. You have to make it like this. Here is the output divided by intermediate state times intermediate state divided by the input. And you take this guy as one of your denominator. And you take here the other way around. Okay? So that the multiplication recover back. Any question about that? This is a trick we usually do, although it's not very common in undergrad. So we do it like this, okay? Otherwise, if you have a second order, if you multiply directly, the issue is that if you have a second order system, you will end up with a fourth order state space model. This is not representative. This is not linear realization. So you have to do this trick to end up with a second order. A matrix is 2 by 2. Okay? So we'll do it now. Let's do it. Now let's multiply together. What's happening? Okay. So let's multiply. Remember, this is S, okay? You got all this. So anything times S squared is double dot, because we're reversing back to the time domain. State space is in the time domain. Plus D1 x dot plus D naught x equal left quasi steady. Any question about that? Okay. I'm doing Laplace inverse, which is very easy. Any Laplace variable gives you 1 dot. Okay, so whenever you have double dot for a thing, or whenever we have differentiation, we define a state, right? So our x1 is x, and our x2 is x dot, correct? We usually do that. And your sought equation, your target equation is d by dt for the x's, is linear combination of the x's plus linear in the input, right? If you have a question, please stop me. I'm doing it. I mean, this is very well known. If you have a question, please stop me. The first equation is trivial. D by dt x1 is x1 dot. x1 dot, or x is x dot. I'm sorry, right? x1 is x. So d by dt for this guy is x dot. X dot by definition is x2. So the first equation is x1 dot is equal to x2. So 0x1, 1x2, 0, right? And the second equation, this guy is simply your x double dot. So please read it from this equation. So it's d naught times x in negative. Here is d naught in negative. d1 in negative times x dot. And 1 times L quasi steady. We are done with the A and B metrics of our aerodynamic, unsteady aerodynamic state space model. Okay. This is the state equation, but we have the output equation. Remember, the output is my circulatory lift. Again, it's also linear combination of the states. This is your state space model plus something times the input. This is your instantaneous output. This is your instantaneous output. It should not depend on your instantaneous input unless you have a D matrix, which means you have a high frequency gate, right? This is simply the high frequency gate. So what you expect to be how much here? How much?
1/2.
The 1/2, right? So again, I multiply here and there. So your L circulatory, this is your output equation, is N2P double dot plus N1P dot plus N naught. Sorry, what's that? X. Right. N naught X. So these terms are easy. N naught times X, here is N naught times X. And N1 times X dot, here is N1 times X dot. This guy, we need to use this equation to get it. So it's N2 times negative D naught X, negative D1 X dot plus L quasi steady. So we'll do it here. So this is N2 D naught, N2 D1, and here is N2. N2 is the 1 minus A1 minus A2, which is the half. And we have a state space model for our unsteady aerodynamics. Please keep it because we will use it in our flutter analysis. We will couple unsteady aerodynamics state space model with the structural dynamics state space model. We have a big state space model governing our aeroelastic system. Then you study its stability in like this. Why? Because the stability should be when the eigenvalues of the entire A matrix cross the imaginary axis simply, right? Would be very simple. This is why we like the state space model kind of writing, because it's very convenient. You want stability, check the eigenvalues of this guy. You want to control, check the controllability and no state feedback. You know, you want to do full state feedback but with one measurement, so check the observability and build an observer. There's a huge legacy that you can exploit if you have this language. Okay? Plus, it's very, very convenient if you have, here is your flight dynamics model or structural dynamics. What's the input to your flight dynamics? And what's the output? For any dynamics problem, the inputs are the forces, right? Forces, so lift a moment, in our example. And the output is the motion. For any dynamics problem, this is the thing, right? We already have a state space model here. We already have, it's built in 175 in whatever class. Now we're getting this. We're having this motion to our aerodynamic system, getting the forces out of here. Now we just build a state space model for this guy. So next lecture we will combine both of them, not for the flight dynamics but for a wing structure, to have a big state space model. So the midterm will be released today. It will be due next Monday in lecture. Okay? This lecture is not included, but last lecture is. And feel free to